First video in Unit 3. Unit 3 is going to be all about polynomial functions. And in Learning Target 5A, we're going to learn about the basics of polynomials and how to graph a few examples. By the end of this lesson, you will be able to determine the degree of a polynomial, the leading term, the leading coefficient, and the constant term. We will also be able to determine what the end behavior of a polynomial is using the degree and the leading coefficient, as well as find the zeros, which are also our x-intercepts, are our roots of a polynomial, and the end behavior, and then use those pieces of information to help us sketch a graph. So let's talk about what a polynomial is. So on the screen, I have the standard form of a polynomial, which looks rather complicated. And we're going to read that in a second, but I want us to first know this, that polynomials only have integer powers. And so the reason that standard form looks as complicated as it is goes back to the fact that polynomials only have integer powers. And we've seen some examples of polynomials already. So in our first unit, we studied linear polynomials, which were our lines, our straight lines, so maybe like 5x minus 3. In our second unit, we studied quadratic functions, which is an example of a polynomial. So we had something like maybe negative 3x squared plus 7x minus 5. And we talked about standard form for both of these. And in the quadratic case, when we had standard form, it was that y equals a times x squared plus bx plus c. And so we had an example of a polynomial here. We had that highest power of 2, and then we had that single x term, and then we had what we called our constant term, since there was no x there. And what we're going to do with a polynomial in general is we're going to expand upon the concept that we learned about with quadratics. And so what standard form of a polynomial looks like is similar to standard form of a quadratic. We are going from the highest power down to the lowest power. And so let's read through this standard form. We have p of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2 power plus this dot 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 represents everything in between that we could keep writing. So that n minus 3 power, the n minus 4, n minus 5, all the way down to we get to the x squared term, which would be that a sub 2 x squared plus a sub 1 times x plus our constant term here. We're going to represent that with a sub 0. You might be wondering, well, why can't I use letters like I did before? Why couldn't I just have that a, b, c, d all the way down the alphabet? Well, the reason is that polynomials just have to have integer powers. So I could have a power that's much larger than the number of letters that we have in the alphabet. So we need a more generalized way to represent that. And since we only have a finite number of letters in the alphabet, I can't just use A, B, C, D all the way down the alphabet. Instead, we're using this notation where we have A with a subscript here. That n is our subscript that matches the exponent power there. So a sub n is attached to that x to the n power, and a sub n minus 1 is attached to the n minus 1 power on there, all the way down the line till we see in the a sub 2 is attached to the x squared term, and the a sub 1 is technically attached to the a to the first term. We just don't usually write that first power, and the x0 here, or the a sub 0 is attached to or multiplied to an x to the 0, but anything to the 0 power is just equal to 1, which is why we don't normally write that x to the 0 power then. And you might be wondering, well, why am I subtracting 1? Well, the reason we're subtracting 1 is that we have to have integer powers only. And if n is an integer, like let's say the integer 100, if I subtract 1 from that, I'm still on an integer and I'm at 99. And then if I subtract 1 from that, I'm down to 98. Subtract 1 from that, I'm down to 97, all the way down to the second, the first, and the 0 power. So that's why we have kind of this funky notation. Couple things to keep in mind, because this can look extremely complicated the first time we see it, is that polynomials have to have integer powers only, and in standard form they go from the highest to the lowest power. And we're going to see some actual examples with some numbers in a second. Let's talk about a few more vocab terms. So the degree of the polynomial is the highest power. So in this case, the degree of this polynomial that we had was n, since n was our highest power. Everything was lower than that because we were subtracting from that n. So we have n minus 1, n minus 2, all the way down, so on to the second, first, and the 0 power. The leading term of a polynomial is the term with the highest power. So if my highest power here is n, then my whole leading term of my polynomial would be this a sub n times x to the n. It's the coefficient part times that variable part of the x to the n. Now the leading coefficient of a polynomial is the number that is from the leading term. So in this case, that a sub n is representing our leading coefficient of this polynomial. And our last vocab term is a constant term. And the constant term of a polynomial is the term with no x. So just like we had before, it was our last term in standard power, which is just going to be that number that is added or subtracted at the end. So for our polynomial p of x, that constant term is going to be a sub 0. So let's look at this with some actual number examples in here. So for each of the following examples, we're going to make sure we have the polynomial in standard form. And if it is not in standard form, we'll be rewriting it in standard form. We will also be stating the degree, the leading coefficient, the leading term, and the constant term. So let's start with our first example. We have f of x equals negative 5x to the fourth minus 10x cubed plus x squared minus 3x plus 2. What do you guys think? Is that polynomial in standard form yet or not? So standard form is when we go from highest to lowest power, and this polynomial is in standard form already since I have that negative 5x to the fourth is my highest power, and then I have the x cubed term, then I have the x squared term, the negative 3x, and the plus 2. So out of all the terms, all the non-zero terms that we have, we're going from highest to lowest power. Now it's not actually necessary to have all those terms in here, but if I do, I want to make sure I'm going from highest down to lowest power. What's the degree of this polynomial? Well, our degree is our highest power. So for this polynomial, our degree is going to be 4, since 4 is our highest power. What's the leading term for this polynomial? Now the leading term is the term with the highest power, so that would be the negative 5 times x to the fourth term. What about the leading coefficient? Remember, the leading coefficient is the number that we get from our leading term. Since our leading term is negative 5 times x to the fourth, then our leading coefficient is going to be negative 5. And lastly, our constant term. What would our constant term be? So our constant term is the term with no x, so in this case, our constant term is that 2 at the very end of our polynomial. Let's look at another example. So in example 2 here, we have f of x equals 4x to the fourth plus x to the 13th plus x squared minus 9x cubed plus 7x. What do you guys think? Is this polynomial in standard form? So in this case, no, this polynomial is not in standard form since we're not going from highest to lowest power. Why don't you guys pause the video right here and rewrite this polynomial in standard form. So standard form for this polynomial has to have the highest power, which would be the x to the 13th. Then we'd have the 4x to the fourth. Then we'd have that negative 9x cubed plus that x squared term, and then plus the 7x. And in this case, I don't have every single integer power from 13 down, but out of all the powers that I have, I'm listing them from highest to lowest power. And this is then going to be a polynomial in standard form. Why don't you guys pause the video and find the degree, the leading term, the leading coefficient, and the constant term for this polynomial. So in example 2, our degree is going to be 13, since that's our highest power. Our leading term is that x to the 13th, since that is the term with the highest power. Our leading coefficient in this case is actually just going to be a 1, since I have that visible 1 in front of the x squared. And our constant term is, remember, the term with no x, and since I technically don't just have a number added or subtracted at the end, there's actually that invisible 0 that's really a plus 0 at the end of that polynomial. Let's talk about a few more things having to do with the degree of a polynomial. So if we consider a polynomial in standard form again, where n is the degree of a polynomial, then we have a couple different types of polynomials based off of what that degree is. So if our degree is equal to 1, then we're looking at a linear polynomial. And these were actually functions that we looked at back in Unit 1. One example would be y equals 3x plus 2. Another example could be y equals negative maybe 10 over 4, x minus 5. So any polynomial with the highest power being 1 there would be a linear polynomial. Now, quadratic polynomials happen when our degree is equal to 2, and this is what we spent all of Unit 2 talking about. So one example could be y equals x squared plus 2x plus 4, and any quadratic function would work as a quadratic polynomial. Now, if our degree is equal to 3, we have what we call a cubic polynomial. So one example could be y equals 6x cubed minus 5x plus 1. So we can see here our highest power is that 3, and this makes it a cubic polynomial. A quartic polynomial happens when our degree is equal to 4. So one example could be 5x to the 4th minus 7x squared minus x. And that highest power again is that 4, which tells us that we have a quartic polynomial. Our last one that has a special name would be if our degree is equal to 5, then we have what we call a quintic polynomial. So one example could be y equals 7x to the 5th plus x to the 4th plus 5x minus 3. Now, if our degree is equal to 6 or higher, then we don't have a special name for it. We just call it an nth degree polynomial. So for example, y equals 8 times x to the 10th minus 9x to the 7th plus 3x to the 5th minus 10x cubed plus 16. Since our highest power here is a 10, so our n here would be equal to 10, we call this a 10th degree polynomial. So it's just for the first 5 cases that we have this linear, quadratic, cubic, quartic, or quintic polynomial. Past that, we would just call it a 6th degree, 7th, 8th, 9th, 10th degree, and so on as we keep going. Next concept we're going to talk about is end behavior, which helps us to categorize the different types of polynomials that we have. So the end behavior of a polynomial is what happens to the far left and to the far right of a graph. Overall, there are 4 options for end behaviors for a polynomial function. This first option here we have is what we call a down-up end behavior, since to the left side the graph is going down, and then to the far right side the graph is going up. Our second type of end behavior is what we call up-down, where instead to the far left the graph is going up, then to the far right the graph is going down. Notice in between the far left and the far right, I just kind of have some squiggles in there, because it really doesn't matter what happens in between, it's just mattering what's happening to the far left or to the far right. Now our third case would be what we call up and up, since both the far left and the far right both go up and up. And then our fourth case would be what we call down and down, since the far left and the far right both are going down in those 2 directions. And how we determine the end behavior is actually based off of the leading coefficient as well as the degree of that polynomial. So the degree and the leading coefficient determine the end behavior. So let's look at these 4 cases then. So that down-up first case that we had from before, this happens when the degree is odd and the leading coefficient is positive. The most basic example of this would be the linear function y equals x. Because in this case, our degree is that 1, since that's our highest power, and our leading coefficient is also positive 1. And we can see from that graph that we graphed back in Unit 1, this is the function y equals x. It has a positive slope that goes through the origin, and I can see here that I have the end behavior going down to the left and up to the right. So although in this example up above with the squiggles, I put squiggles here because we don't really know what happens, but in this basic example of y equals x, we know that that's just a straight line with positive slope. But it still has the same end behavior as the graph up above here with all the squiggle lines in between. Since to the far left it goes down, to the far right it goes up. Now our second case here of the up-down happens when the degree is odd. So the degree is still odd just like in case 1, but now the leading coefficient is negative. So this would be what happens if I have the basic example y equals negative x. So here, my degree is still equal to 1, which is an odd number, but my leading coefficient now is a negative 1, which produces a negative slope on my graph. And so I can see to the far left I'm going up, and then to the far right I'm going down. And that matches up with the same end behavior that we had up here in our general example. I just don't have the squiggles in between since this is just a linear function, so I get a straight line for my basic example. Now if we look at our third case of being up and up, that happens when our degree is even and our leading coefficient is positive. Now the most basic example of this guy would be our quadratic function y equals x squared. And here I can see that my degree is even since my degree is 2 and my leading coefficient is a positive 1. And we know this graph from our last unit. It's our parabola that's facing upward, and I can see from this graph that to the far left and to the far right the graph goes up in both directions. Just like in our most general example up here where we have up and up with the squiggles in between. Again, those squiggles in between really don't matter. It has nothing to do with the end behavior. The end behavior is literally what happens to the far left and to the far right of our graph. Now our fourth case here is the down and down, and that happens when our degree is even and the leading coefficient is negative. So our most basic example of that would be y equals negative x squared. And we can see here our degree is even, it's a 2, and our leading coefficient is that negative 1. Now this, we knew from our last unit, is a reflection of the parabola over the x-axis, so our parabola is now facing downward. And I can see that both to the left and to the far right, the graph is going down and down, just like it did in our general example up above. And these are the only 4 cases that we have because my degree is either going to be even or odd. And so in our top row here, this is what happens when our degree is odd. In the bottom row here, this is what happens when our degree is even. And then for our leading coefficient, I either have a positive or a negative number. And in this first column here, this is what happens when our leading coefficient is going to be positive. And in the second column happens when our leading coefficient is going to be negative. And so these are the 4 cases that we get. If our degree is odd and our leading coefficient is positive, then we're in this first case of down up. If our degree is odd and our leading coefficient is negative, then we're in the second case of up down. If our degree is even and our leading coefficient is positive, we're in this third case of being up and up. And if our degree is even and our leading coefficient is negative, we're in this fourth case of being down and down. And I think it's really helpful to remember the basic example and kind of, since we know what these 4 graphs look like in our mind already, it helps us think about, okay, well, since I have a straight line with positive slope in case 1, then I'm going down and then I'm going up. So instead of trying to memorize what all of these match with, if we can think about what the basic examples look like, then from there we can figure out what the end behavior is by sketching that graph to the side. And we're going to see in examples that I end up sketching this graph a lot, where I just sketch the basic example and then determine the end behavior from there. Let's look at some of these as examples. So for each of the following functions, we want to state the degree, the leading coefficient, and then determine the end behavior. And I'm going to in fact scroll back up so we can have all of those cases here. So let's look at our first function. We have f of x equals 2x to the 8th minus 4x plus 5 as our polynomial. Why don't you guys pause the video right now and decide on what your degree and your leading coefficient is. So in this case, our degree is going to be 8, since that is our highest power, and our leading coefficient is going to be 2, since that is the coefficient that's attached to the highest power. So our degree here then is even, and our leading coefficient is a positive number. So this is like y equals x squared then. Sorry, that got a little messy. Let's clean that up. So this is like y equals x squared, which we know that that graph is a parabola that faces upward. And so from that graph, I can see then that my end behavior for this polynomial function, 2x to the 8th minus 4x plus 5, is going to be up and up then. And if we were to graph it, I wouldn't have a nice smooth U-shaped curve, but on the far left and the far right, the graph would be going up in both of those directions. So this matches what we have up here in case number 3. And I'll kind of keep track of the cases on the side. Now, I don't ever want us to say that our answer is case number 3. Our answer is what the direction is. So our answer is always either going to be down, up, down, up, or down, down. And so in this first example, our end behavior is going to be up and up because our degree is even. And our leading coefficient, I'm going to shorthand leading coefficient with LC, is going to be a positive number. So if we were ever asked to justify, that would be our justification. Let's look at our next example. So in our next example, we have f of x equals negative 4x to the 5th minus 2x squared plus 7x plus 1. And we want to determine our degree and our leading coefficient. Why don't you guys pause the video and determine those two? So our degree for this polynomial is going to be 5, since that is our highest power, and our leading coefficient is going to be negative 4. To figure out our end behavior, we want to determine if our degree is even or odd. 5 is an odd number, and our leading coefficient in this case is negative. So this is like our basic example, y equals negative x. Since our lowest power that we could have that would be odd would be just x to the first, and our leading coefficient there is negative. And we know what this graph looks like. It's a straight line with negative slope. And so from that graph, I can see then that my end behavior would be up to the left side and then down to the right side. And so if we wanted to justify that, that would be because our degree is odd and our leading coefficient is negative. And that would be matching that case number 2 that we had from up above. All right, let's look at some more examples. Why don't you guys pause the video and do example 5 on your own first, and then we'll check it together. So let's look at example 5. We have negative x to the 12th minus 11x to the 8th minus 2x to the 5th plus 3x squared. So in this case, our degree is 12, since that is our highest power, which is an even number, and our leading coefficient is negative 1, which is a negative number. So if I think back to my basic examples, this is like y equals negative x squared, which we know is a parabola graph that's facing upside down. So from there, we can determine that our end behavior for this polynomial would be the same as the end behavior for y equals negative x squared, which is down and down. And if we wanted to justify that, that would be because our degree here is even and our leading coefficient is negative. Now let's look at our last example of this type. So we have f of x equals 10x cubed minus 7x squared minus 8x minus 12. Why don't you guys pause the video and do example 6? So our first thing in example 6 is our degree, which is 3. Our leading coefficient is 10. So I have an odd degree and a positive leading coefficient. So this is going to be like y equals just positive x, which we know is a straight line with positive slope. And the end behavior on this straight line would match the end behavior of our polynomial in example 6, which is down and then up. And if we wanted to justify that, it's because the degree is odd and the leading coefficient is positive. Let's talk about one other concept before we start putting these all together into a graph. So the last thing we want to talk about is actually something we've addressed before, but let's look at it from the lens of a polynomial. So let's let p of x be a polynomial and b be a real number. Then the following statements are all equivalent. X minus b is if x minus b is a linear factor of a polynomial p of x, then b is what we call a 0 of that polynomial. B is also called a root or a solution of the polynomial equation p of x equals 0. And b is also what we call an x-intercept on that graph of y equals p of x. And what this means is that all the terms 0, root, and x-intercepts are all interchangeable, just like they were before in our last unit. Okay, I realize I do have one tiny typo on there. It's not going to be that b is an x-intercept, it should be that b comma 0. Since it is a coordinate pair, there is our x-intercept. And we're going to use this concept that we had in example 2 of zeros, roots, and x-intercepts all being the same to help us actually graph a polynomial. So let's look at our first example of graphing. So in example 7 here, it says, consider the polynomial p of x equals x plus 2 times x minus 1 times x minus 3. And you'll notice that I have quite a few questions before I actually get to the graphing part. And the reason we have this is how we graph polynomials is going to be different than what we did in our prior 2 units. We no longer have a parent function to work with since our degree is constantly changing. And so if I were to try to think about this from a parent function perspective, we'd have to have an infinite amount of parent functions since I could have any integer power as my degree. So instead of thinking about it from a parent function perspective, we're going to instead think about what are our zeros, what are our x and our y-intercepts, because we definitely need those on our graph. We also want to think about this concept of end behavior so that we can get an overall picture of the graph, and then we're going to use that information to sketch. And in the coming sections, we're going to start to add in more pieces of information. So right now, the 2 examples that we're going to do are more basic examples, and as they get more complicated, we're going to learn some more terminology and more pieces of a polynomial that go into play. So looking back at example 7, one thing I want us to notice is that this polynomial is actually in factored form. This is not in standard form because I have each of these linear factors. I have this x plus 2 times the x minus 1 times the x minus 3. And that's okay. In fact, to graph it, it's actually easier to have my polynomial in factored form. And the reason is, in part A, we want to find the zeros. Well, to find the zeros of a polynomial, I'm going to set this function equal to 0. So I have 0 equals x plus 2 times x minus 1 times x minus 3. And what we're going to do is apply the zero product property, which we learned in our last unit, which says that if I have a product of things that are multiplied that equals 0, then I can set each factor equal to 0. So I have 0 equals x plus 2, 0 equals x minus 1, and 0 equals x minus 3, and I can solve each one of these. So for our first one, we'll get x equals negative 2. Whoops. So x equals negative 2 is a 0. My next one would give me x equals positive 1. And for the last one, we'd get x equals positive 3. Those right there are all of my zeros of this polynomial p of x. Oops. And so we used the skill of being in factored form already, which allowed me to immediately apply the zero product property and solve for each one of those zeros. Now, if we were in standard form to begin with, then we would actually have to change to factored form before we could find the zeros. Now, in part B, we want to find the x-intercepts of this polynomial. Well, we just learned and kind of reviewed from before that the x-intercepts are equal to our zeros, so I don't have any more work to do. I actually already have my x-intercepts. They're coming from part A. Since in part A we found our zeros of negative 2, 1, and 3, the difference now is because they're x-intercepts, I just need to write them as coordinate pairs. So I have negative 2, 0, 1, 0, and 3, 0, and those will be our x-intercepts. And so part B is less about finding something, but actually about understanding what the vocab terms mean and the fact that x-intercepts and zeros are the same concept. Now in part C, we need to find the y-intercept of our polynomial. Well, why don't you guys think all the way back to Unit 1. How did we find y-intercepts for any function? Well, to find a y-intercept, we're always setting x equal to 0. The reason being is in a y-intercept, I always have 0, some number that I'm trying to find. So if I set x to 0, then I'm finding really what p of 0 is equal to, which would be 0 plus 2 times 0 minus 1 times 0 minus 3, which if we simplify that down is the same thing as 2 times negative 1 times negative 3, which when we multiply that out is going to give us a positive 6 then. So that means that our y-intercept is at 0, 6. Now our next part that we need before we can graph is to determine the end behavior. Well, the end behavior for our polynomial is based off of the degree and the leading coefficient. All of that comes from our leading term though. And something tricky about this example is because we're in factored form, it's a little bit harder to find my leading term. But we can still find it. To get from factored form to standard form, I would want to FOIL everything out. So if I'm trying to go to factored form to standard form, I would want to be FOILing everything out, but it's not necessary to FOIL everything because my leading term is just the term with the highest power. So what I want to factor out is all of the terms with the x's in it, and anything that would potentially be in front of the parentheses. But if I FOIL out all the terms with just the x's in it, I would end up with an x cubed plus, I don't know, some other stuff if I were to keep FOILing. Now I don't care what the other stuff is, I just care about the leading term, which in this case would just be the x cubed. And that's coming from taking x times another x. And so then from here we can see what our degree is and what our leading coefficient is. Why don't you guys pause the video and find your degree and your leading coefficient? Well, our degree here would be 3, and our leading coefficient would be a positive 1. And so in this case, then I have an odd degree and a positive leading coefficient. What type of end behavior would that give us? Well, if I have an odd degree and a positive leading coefficient, this is like y equals x, which would just be our straight line with positive slope. So our end behavior is going to be down, up. And in this problem, we are asked to justify it, so we need to explain it just like we were doing before, but that would be because the degree is odd and the leading coefficient is positive. Now what we're going to do is we're going to put all of this together to help us sketch a graph. I'm going to have to cover up the original problem there. And on here, I want to make something very clear. We're not formalizing this graph at all. We are very much sketching an approximation of what the overall picture looks like. So I have to have certain key information that is correct on there. I need my x-intercepts and my y-intercepts to for sure be correct. Besides that, I'm not going to have any other exact points on this graph, and that's okay. I'm trying to sketch what an overall picture of this would look like, and that's where the end behavior is going to come into play. Let's start with our intercepts. So I'm going to plot my x and my y-intercepts. You'll notice something on this graph though. I have no grid lines, and in fact, I don't want to be using graph paper. It would be very challenging to try to do this on graph paper because the boxes are so tiny, and I'm going to want to space this graph out as much as possible so I can see what's happening from an overall perspective. So because of that, since I don't have any graph paper on here, I need to create my own tick marks. So if I have an x-intercept of -2, 0, well, there's, let's say, -1, there's -2, and I'm going to put that point. And of course, I'm going to be labeling these so I know where they're at. My next x-intercept is at 1, 0. Well, let's go positive direction 1, and I'll put a point there. My next x-intercept is at 3, 0, so that was 1, 2, here's 3, and I can put a point there as well, and I'll label that with a 3. So my x-intercepts are on my graph. I absolutely need to put the tick marks on here. If I don't have the tick marks and just have random points, even if the random points are labeled, I need the tick marks on there to understand how far we've spaced. Now for my y-intercept, we're up there at +6, which I want to put way up at the top of this so that I can space out the graph. So I've got 1, 2, 3, 4, 5, +6, way up here. And one thing we're going to notice is that the axes on the x-axis and the y-axis, they're spaced differently. But that's okay. I really want to space out my x-intercept so that I can easily draw what's happening in between. But my y-intercepts, they're going to become quite large numbers. And so because of that, I might need to space them out a little bit less so that I have room on my graph. Now that I've got my x and my y-intercepts plotted, the next thing I want to use is the end behavior. Well, from the leftmost part of the graph, it says that my end behavior is down. Well, my last x-intercept here is -2. There is no way that my graph can turn back around and cross the x-axis again because I don't have another x-intercept to the left of -2, which means since my end behavior is down from the far left side, that the graph is going to go down to the far left of my leftmost x-intercept. Same thing for my end behavior on the right side. 3 is my largest x-intercept, and I can never have another x-intercept again, which means the graph can't turn around and cross the x-axis. So from the rightmost side, my end behavior is saying up, so my graph is going up from 3 then. Now I don't know exactly how it goes up or down. It might squiggle a little bit. It definitely doesn't cross back on itself because these are functions, so the graphs would need to pass the vertical line test. So I'm just drawing this kind of down curve and this up curve to represent down and up. And the reason I know that that happens from -2 and from 3 is that -2 is my leftmost x-intercept, and my end behavior from the left side is down. 3 is my rightmost x-intercept, and my end behavior from the right side is up. Now from here, I have to make the graph connect together, and I know that these 4 points are on my graph, and so somehow they need to connect together while still being a function. So my graph has to pass the vertical line test, which means from -2, the next point that it would reach would be 0,6, so it's going to come up here, reach 0,6, then the next point it would have to reach is this +1, and then from here it would have to reach, it would have to reach that +3 then, and I have a couple options. It could come up and over, like this dotted line that I'm going to draw, or it could come down and around like this dotted line. And because I know where we're going in the next section, this does cross through the x-axis, and it does take on this kind of bottom route of creating a little valley-like shape in the graph. And we're actually going to see in Learning Target 5B why that happens. But for now, all of our x-intercepts are what we say crossing through the x-axis. So I'm crossing through at -2, I cross through at 1, and I'm crossing through at 3. And this is a sketch of the graph. Your graph is going to look slightly different than my graph. But what has to be true is that from the leftmost side I'm going down, from the rightmost side I'm going up. The only places I'm crossing the x-axis are at -1, 1, and 3, and that my graph is also touching my y-intercept of 0,6. So one thing that could not happen that I'm going to draw in with black marker here is that from -2, there's no way to come up, come down, and then go back up to 6. This cannot happen because it's creating more x-intercepts right here that I'm circling. So I know that this does not happen on my graph because I have only 3 x-intercepts. And so if I were to create a graph that crosses the x-axis more times than just at those 3 places, then I'm not graphing the correct polynomial because I'm creating more x-intercepts that are not there. I only have these 3 x-intercepts from part B. All right, let's look at another example. So this will be our last example. We have the polynomial f of x equals -2x cubed plus 2x squared plus 4x. Now the difference here is that we're actually in standard form. And I can't solve for the zeros unless I'm in factored form. So we need to figure out how to factor this. You guys notice anything about how to factor this polynomial? So the first thing I notice is that I want to take out my greatest common factor. What is the greatest common factor for f of x? So our greatest common factor here would be a -2x. They each have an x term in them, and all of the coefficients are divisible by 2. The reason I'm taking out the negative sign is that I want my leading term of what's left over to always be positive. And when we factor out the -2x, we're left with an x squared minus x minus 2. Now from here, I can factor that further since I have a quadratic. So I still have the -2x on the outside. How does x squared minus x minus 2 factor? Well, that would factor as x minus 2 and x plus 1. Now that we're in factored form, to find the zeros, I'm going to set the factored form equal to 0. And then use the zero product property from there. Why don't you guys pause the video and find all of these zeros for this function. So to find the zeros, if I use the zero product property, I get -2x equals 0. I get x minus 2 equals 0. And I get x plus 1 equals 0. From here, I'm going to solve for x in each case. On the first case, when I divide through by -2, 0 divided by a non-zero number is always going to be equal to 0. In the second case, I get x equals +2, and on the last case, I get x equals, not 0, I get x equals -1. And these are all of my zeros then for my function. In part B, we want to find the x-intercepts. Well, Our x-intercepts and our zeros are the same thing, so I'm just going to change each one of these into a coordinate pair. So for the first one, I get 0, 0. For the second one, we get 2, 0, and then we get -1, 0. I want to remind you guys that x-intercepts are always the number, 0. And so that's why the 2 and the -1 are in the x spot, and technically it's that x that's 0 coming from this 0 up above. Now to find our y-intercept, I'm going to have to do some algebra with this. So to find the y-intercept, we're setting x equal to 0. Why don't you guys pause the video and find your y-intercept? And it doesn't actually matter if you use the standard form or the factored form. So to find our y-intercept, I'm going to set x to 0. I'm going to go ahead and use the standard form. And so I'd get -2 times 0 cubed plus 2 times 0 squared plus 4 times 0. So really I just have 0 plus 0 plus 0, and so I'm just getting 0 out. And that actually lines up with the fact that I knew before I even started part C that I have to have a y-intercept of 0, 0, since 0, 0 was an x-intercept. And 0, 0 is the one point that's both an x and a y-intercept, and since it's only possible to have one y-intercept, then because 0, 0 was already an x-intercept, it had to be a y-intercept. Now the last thing we need to find is the end behavior. Why don't you guys pause the video and find the end behavior in part D. So for our end behavior, we need to look at our degree and our leading coefficient. For this guy, since we started off with a polynomial in standard form, I can see my leading term is that -2x cubed, which I could also get if I were to FOIL out my factored form to get back to standard form. And I'd be multiplying the -2x times the x, which would give me a -2x cubed then, as my leading term. From that leading term, we can see that our degree is equal to 3, and our leading coefficient is equal to -2. So I have an odd degree, a negative leading coefficient, which is like a function y equals -x, which tells me that my end behavior is actually going to be up, down. And we were asked to justify it, and so my reasoning would be because my degree is odd and my leading coefficient is negative. Now the last thing I want to do is I want to use all of this information to sketch the graph. So I'm going to start by plotting my x-intercepts. So I have my x-intercepts at 0, 0, so that's right at the origin. Again, I don't have any graph paper on here, and I don't want any graph paper, so I'm going to create this 2, 0 by drawing 2 tick marks to the right. So that's at 2, 0. And then I also have -1, 0, which goes to the left -1. From here, I would put my y-intercept on there as well, but that's already on my graph since it was an x-intercept. The next piece of information we have is the end behavior. Why don't you guys pause the video and use the fact that our end behavior is up, down, and draw what's happening to the far left and the far right on this graph. So since our end behavior is up, then down, so to the leftmost side I'm going up. Since -1 is the leftmost x-intercept, I'm going up from there. And then the down piece is representing the right side, so the rightmost x-intercept is the 2, which means I'm going down from that 2. And again, the reason that happens is the graph can never turn back around after these x-intercepts because I don't have any more. -1 was the furthest to the left and 2 was the furthest to the right. Now from here in between, I get to play, honestly, connect the dots. And because right now we're saying that all of our x-intercepts cross through, then I know I go through -1, I have to reach that 0, 0, cross through again, and then come back to that 2, 0. Now, of course, because I don't have any other points on this graph could come way down here, then cross through and come way up, and then come way down. I'm just drawing kind of the most basic example that we have here. But again, your graphs are going to be slightly different than mine. We just have to make sure that we have only the x-intercepts that we should. So I only have -1, 0, and 2 crossing at the x-axis. And that, of course, my graph reaches all those points as well as the y-intercept, and that our end behavior lines up from there. We're going to continue talking about more examples in our next section as we learn about a couple more pieces of vocab and build upon these concepts.